Welcome to this lecture on modern digital communication techniques. In the last couple of lectures, we have seen the basics and fundamentals of the differences between a digital and analog communication system. And in the last lecture especially, we saw the critical aspects of a digital communication system, or the fundamental aspects which one must get into. And amongst a few things, we did say that noise is one of the important aspects which should be handled. Today we continue a bit more in trying to explain to you a typical way of designing systems, a typical way of layering, architecturing, so that you can divide and conquer a big problem and divide it into smaller problems, and finally solve each of the problems and finally conquer the bigger problem. Today's digital communication systems are very complex systems. So if you would see when it all started, one of the earliest communication systems, if you would think of, if you don't think of a communication system, rather a mode of communication, it would be smoke signals. That was historic. There were in the Africas, there would be drums, rolling drums or talking drums, which could send messages across hundreds of kilometers through methods of relays. Well, relays are relatively modern terminology, but that was the way it was being done. So if you look at today's technology, where myriads of devices, from smartphones to laptops to computers to all kinds of devices, to sensors to machines, they are all connected almost in a single network, compared to those days where it were very basic. But the need of communication was always there, and because of that need, we have driven all the way, and we are in a very advanced stage of communication, where almost anywhere we want, we can set up a communication network. We can connect almost any device, and we are also able to provide almost any time communication. We have gone into space. So if you look at these various domains of communication, one could ask that, okay, what has been the driving factor for all of these things, and who has been doing all this activity? So there have been many different people who have been contributing, and amongst them, in the modern era, one of the pioneer centers was the Math Center at Bell Labs. So from there started many contributions of modern wireless communications. Of course, we are not debating history about who was the first, who was the second, and so on and so forth. But what we are talking about is the modern way of looking at things, and the way of breaking down into things and solving each one. So this Math Center, and once we pick up this name, what it tells us is it builds up certain mathematical models, of course, and that's what we said in the beginning of the course. So the way they structured the system was very elegant, and thereon things became very nice. So one of the things which this center gave us was information theory, which is a closely related subject. This particular name is for a subject of its own, it's a course of its own, and a huge amount of literature has been developed. And if you look at digital communications are modes of achieving things which are prescribed by this particular theory. So when we study our particular subject, information theory would be scattered here and there, and it will be the driving principle. So just to keep in mind, information theory is one of the mother subjects of our particular domain. And two important ideas, if you look at two important ideas which helped us through all of this, is one, if you would summarize, is to view all communication systems all communication sources, be it speech, be it image, be it video or text, whatever it is, as represented by binary sequence. So this is one of the important things. It said that whatever is the source, can we imagine them to be giving out binary sequences? So in the previous lectures, we have given some examples of what we have today. So we have to think of when these were not existent, when things were pure analog sources, where they were images. So if you could think of that time, and at that time thinking of such an idea was quite revolutionary, that you think of from these analog signals directly a binary sequence which could represent these things. So this is one important idea. And the second was to design communication systems that first convert the source into a binary sequence and then convert the binary sequence into a form that is suitable for transmission over a particular physical media. Now, this is what we had explained in the previous discussion, that almost intuitively we said that if you look at what things are today, they are in this form. This is what we had explained in the last discussion. If I try to bring out in this particular picture, this particular description, we said that there are symbols. So, there is a discrete, and these would be common, but this would go into different physical channels. So, that is what is mentioned over here. So, two important ideas. One is to view all communication sources as represented by binary sequences, and then to design communication system that first convert the source into a binary sequence, of course that is there, and then convert the binary sequence into a form suitable for transmission. So, this is how you could carry on with your sequence of things. And then one would define, we had defined it yesterday, a digital communication system as. So, now we define digital communication system. By definition, these are communication systems that use such digital sequences. So, now if we combine these two things, we more or less have a digital communication system description. That means, it says that first you convert a source to a binary sequence. Once you have converted the binary to a binary sequence, now you again convert it to some form which is matching with the physical media, and then you define digital communication as a communication system which uses these binary sequences or these digital sequences. Now, these digital sequences could be binary, or they could be multi amplitude level as well. Well, so these are some of the important aspects which we should keep in mind as changes as one moves from analog communication to digital communication system. The other important aspect that we would encounter in designing of things is our interfaces. So, although in analog communications you may have studied components and step by step development, but here we define interfaces, and I will explain shortly that why do we do it and what is the necessary and how does it help us. So, if we think of a source, so let there be a source followed by a source encoder, and then there is this channel encoder, then the signal goes out into the channel, back to at the receiver there is this channel decoder, and then again this source decoder. Back here the destination. So, this is a very broad diagram or a block diagram of a typical transmitter receiver structure that one can think of. Things can't be simpler than this. So, if we look at this and what we have written before, there is one-to-one correspondence. So, there is sources to be converted and then they are to be transformed to a physical form. So, you have a source here, you get binary interface, So, by what we mean is that here there are a sequence of zeros and ones, and then these are converted in some form because of this physical channel and again decoded, and it is source decoding is done over here. So, if you have this interface, there are many advantages of having this particular interface. Amongst many different advantages, one clear thing we need to see over here is this source encoder. When it gives an output, it generates a sequence of zeros and ones. Once it does that, it need not bother about what lies on that side. So, this is almost encapsulated, right. We can think of as if there is a communication system, source converts to a sequence of zeros and ones, then it goes into something which we can call the channel, integrated channel, and then this sends out again a sequence of zeros and ones. The job of the source decoder would be to take these inputs and generate the output at the destination. So, when we have this interface, we can define that the channel encoder takes a particular sequence of zeros and ones, not a particular, takes a sequence of zeros and ones in a particular rate. Rate means it talks about the time interval of generating zeros and ones, and it generates outputs. So, some of the different contributions that can be taken from this is that source encoder need not bother about what the channel encoder does. It can do its job independent of the channel encoder. Similarly, the channel encoder need not worry about what the source encoder does only if it knows that there is this particular sequence or there is a sequence of zeros and ones. When you talk about binary interface, you say I am going to get zeros and ones, that is it, and it will work on this sequence and produce a certain output. Now, if this is again another binary channel, it is going to produce a binary output. If it is a waveform channel, it is going to produce waveform outputs, and so on and so forth. So, these two need not worry about what each one does except knowing about details of this interface. Same goes over here. This is one part. The second part would be that when one designs the source encoder and one designs the source decoder, at that point the decoder need not worry about what has happened here. It simply knows that I am going to get some binary sequence and I have to produce a particular kind of output. So, it can be designed with the idea that as if these signals are going into this, there could be errors, there may not be errors, that depends upon the particular type of model of the channel that we want to incorporate. So, this would be the dual of this particular box. So, they could be designed and implemented by a group of people quite independent of this thing. In other words, if there is, let us say, speech source, you can define the speech encoder as well as the decoder, and the output can be sent through a wireless channel, through a twisted pair, or through a coaxial or through optical fiber, where these things, these two parts can remain common, where these parts will be different depending upon the situation, depending upon the type of channel. Continuing further, so if we look at why or the reasons why communication systems now have a digital or a binary, you can say, instead of digital you can simply say binary interface between a source and channel, let us say. Why so? A couple of things come up. One is digital hardware is cheap. It is reliable as well, and it is miniaturized. That means you can get in very tiny form. This is another one of the big advantages. The second thing, as we have just said, the source and channel coding can be done independently if interfaces are standardized. So, by standardized we mean that if this is very well defined, different channel encoders can work on the same source encoder and vice versa at this particular point. Standardized means well defined, well explained, well accepted by a lot of group of people. And the third, which is one of the very interesting things due to Shannon, what he said is that if a source can be transmitted over a channel in any way at all. So, that means what he says, that if a source can be transmitted to the receiver, that means if it can be communicated at all, in that case it can be transmitted using a binary interface. Between the source and the channel. So, this is also an important statement which he made, and that is based on the particular kind of description that we are going through. So, with this logic and justification, what he stated is that if at all there can be communication between the source and the destination, it can be done through binary interfaces. That means, if at all you can communicate, you should be able to do it through binary interface, and then it leads to the point that if at all you can communicate, you should do it through binary interface, because there are several advantages, right. So, this is the last thing which talks about it, and in some places you will find it also being mentioned as source channel separation theorem. It is not a theorem as such, but it is a statement in that sense, which says that the channel is different and the source is different. So, if anything can go through, I can always send it through some binary mode. Okay. So, why this particular thing of standardized interfaces? Now, as we just mentioned in the beginning of this particular discussion, that if you look at today's complex systems, let us say the communication systems are pretty complex, the networks are pretty complex, because there are many different things working together. And if you look at even the PSTN, that is the public switch telephone network, that is also very complex for your signal from one point to go to another point, and the way signals travel. Now, to maintain these kind of systems, to make it scalable, to manage it, you need to break it down into parts. And further, for such complex systems to work successfully, one should have some very simple fundamental theorems or philosophies or principles which make these things work. So, when you look at some very simple principles and theories which make these things work, what you do is that you look for such very simple things and you build smaller things, you build up together and you make a bigger thing. Now, even if you have a very big system where small things can come in at any place, you need to have a way of plugging things together. So, that is why we need to have these standardized interfaces, because the things are very complex. You have complex networks like PSTN, then you have the internet, right? In order to handle them in an easy way, you talk about you talk about standardized interfaces. So, a standardized interface allows a user or an equipment on one side of the interface to ignore all details about the other side of the interface except for some specific interface characteristics. So, this more or less tells us what we have already explained here, that a standardized interface allows user or equipment on one side of the interface to ignore all details about the other side of the interface except for some specific interface characteristics. So, if you look at this, when the source coder is being designed or being implemented, it takes a source and produces a sequence of zeros and ones. That is it, because it knows the next one is going to take the sequence of zeros and ones, right. When it connects to a particular channel encoder, when we say specific characteristics, that means that would be specific realizations. It could be that there is a serial input, it could be parallel, it could be burst. So, depending upon such specific interfaces, it is going to make outputs be available in such manner. If it is burst, then there would be some words and there would be some controller pin which would be activated and it would send a few bits. If it is parallel, again it would send the bits 1, 2, 3, 4, let us say 8 in a particular period of time, periodic signals. And if it is serial, it would be continuously sending the streams of zeros and ones, and somewhere between the two there would be an initial synchronization. Thereafter things would be happening as it is. So, this needs to know the specific interface characteristics. So, once it knows the interface characteristics, that is it. So, that is what it says. It does not need to know anything more what this channel encoder is going to do with this particular output. So, that is what is being said over here. So, that is what we have already explained. And the other important thing which we need to look at is the concept of layering. So, layering, if we think of layering, is as I have already mentioned, that you want to break it down into small parts. So, basically layering is about breaking into logical smaller parts, but not just breaking into random parts, but which are meaningful. And as we go through, we will see the different layers of communication system as we travel down through the course. So, we have already talked about one kind of a broad level layering over here. We can look into further details. So, if we are talking about the source, so let there be some input waveform, and it would go through a sampler. In the same fashion as we have discussed the higher level one, the sampler is followed by a quantizer, is followed by a discrete encoder, and a discrete encoder sends out signal to the binary interface which we had described before. So, we have defined this binary interface before. So, we will write what we see there. This whole thing that it sees could be thought of as a binary channel. This is a bit different compared to what we have discussed earlier. I will explain that. There will be this discrete decoder or table lookup. Sorry, the table lookup comes over here, followed by the analog filter, and then you have the output waveform, right. So, now if we see this earlier picture, if we come at this particular picture, I had briefly stated over here. So, now we are actually encountering that situation. So, if I look at the situation at this point, we can say that the output is an analog sequence. Because this is a sampler, it converts this analog waveform. So, it will be sampled at specific points, and the output that goes is 1, 2, 3, maybe a 4, 5. So, as if this has been quantized, right. So, this is the kind of sequence that goes through this particular interface in this direction. Same would go out from this. However, there is a slight difference that the levels that goes out could be specific levels. So, because this is a quantized version, and then the analog filter. So, basically one could expect an output from here, which is like this, and then this, then this. The job of the analog filter would be to make it continuous. It's kind of D to A conversion you can think of. So, its job would be to reconstruct this waveform, right. So, that is how it is going to happen. And if I look at here, what we are going to get is a symbol sequence. Why is it so? Because these will be passed through quantizer. A quantizer would mean that you are having different levels. So, each level could be assigned a particular symbol. This could be, let us say, A1, A2, or A, B, C, D, A3, and so on. So, what going out is basically a sequence of A1, A2, A3, maybe A4, A4, and so on and so forth. The decoder is similarly going to give such sequences or levels which were there. Those sequences would be converted to signal levels and would be sent out. So, this is a symbol sequence. The discrete encoder would map this particular symbol to a particular sequence, which depends upon the type of encoder. Now, if you are not doing any special encoder, a very simple straightforward encoder would be a PCM encoder. That means you would put 000 for the level 0 and 111 for the maximum voltage level if there are 3-bit quantizer, and you say that this is uniformly quantized, and whatever bit sequence comes out of it goes out of the encoder. Whereas, if you have a source compression technique which uses some of the probabilistic characteristic of this particular source because of this particular waveform, it is going to produce a binary sequence which is not necessarily the same as corresponding to the levels of these particular symbols that we have. So, these could be binary sequences, could be compressed or could be uncompressed, depending upon the type of application. Generally, we have a compressed sequence output at this particular point. So, now if we carefully look at this particular picture at hand, if we want to see the system at this point, if we want to see the sequence at this particular point, we can say that this whole thing is a channel which is a symbol sequence. If I am going to see the system here, I can say this whole thing is a channel where the input is an analog sequence, the output is an analog sequence, and if I put a boundary here, I would say the whole thing is a channel where analog signal goes in and an analog signal comes out, right, and the analog communication part of it would happen somewhere there, would happen somewhere in this part. So, all we are trying to see is that by virtue of breaking into different layers as we have defined and defining very specific standardized interfaces, one can break down the problem into smaller parts, handle that problem independent of what module is following it, and just depending upon the type of specific interface that lies in between. So, for example, this sampler and analog filter would work hand in hand, these two would work hand in hand, and these two would work hand in hand. We stop this particular lecture at this point. We continue further in the next lecture, and finally, we will start talking about source encoder in later lectures, and we will also cover these aspects in the upcoming lectures from now. Thank you.